Then welcome back. And yeah, I will now go a little bit faster through everything. I think I have talked a lot about forecasting in general. Okay, let's talk about the properties again of this exponential. Oh, my misspelling always. So, yeah, this you quite often use if you, by just looking at your data, you do not see more or less directly a trend where you can say, well, on average, we have grown by 2% or something like this. Also for short-term forecast. And yeah, this little sentence here, this is then the hard part. Well, what would be a good alpha? And for this, I always would recommend, if you use this method, since using a computer, it doesn't matter which number you choose, then go just smoothly to through this interval, just test 1, 0.1, 0.2, and so on. Look at the data, playing with the data, and then maybe you obtain a good choice for it. And of course, the advantage compared to the moving average is that you have somehow a parameter where you can play, well, how important should be within my forecast process the valuation of the current or the latest data by choosing a small or a large alpha. Okay, then I think through this I can go quite fast because I've done this always in macroeconomics. Of course, averaging a growth rate is also a general way how to forecast data because in many economic processes we assume a standard growth process, and then as I have shown it at the beginning, this one that we assume or also quite often see that we see in economic data such an trend growth rate. Yeah, and again, this should be here. That you remember this. Using just the arithmetic mean is not the right way to do it. But I think we have also 1 or 2 exchange students, and I don't know if you already know this. So the growth rate, when we calculate this, is just 10 over 5 minus 1. And here, of course, we have a 0 growth rate. This we can copy. Let's reformat this. Oops, percent. And then, of course, since I have chosen the numbers like this, we obtain the same average growth rate for both time series. But of course, you know that we have to take the geometric mean of the growth factors and then subtracting 1. So let's therefore factor A, let's calculate these two, and growth factor B. This would be then the growth rate plus 1. Oops. This growth rate plus 1. And now taking the geometric mean of the growth factors. And then the average growth rate is then the average growth factor minus 1. And then you see here the significant difference. That one is roughly 0.2, while the other one is 0.4, while the other one is, of course, still 50% if both growth rates are 50%. Then let's do I obtain this here? Oops, like this. And oh, have to move you out. And this one. Oh, fix here. Tip. And here we are. Okay. Yeah, this, you know, the average growth rate is the geometric mean of the growth. I have written it down already down there. Then I do not know this again. Do not need this again. But the idea behind this is, of course, you ask for the number using your starting point with which constant growth rate I have to grow n times in order to reach my last data point. And then if I have this number, of course, then I can directly forecast all my values. Okay, again, what shall we do? The quarterly average growth rate, historical trended data, and then calculate the aggregate revenue per year. This we have also already done for the exponential smoothing. Subsequently, forecasting then the year 2023. And of course, having this growth rate, we can, of course, here also forecast all quarters using this quarterly growth rate. Okay, then let's do this. This is growth rate 2. Let's say this is growth rate 1. Oop. No. Growth factor would be just the ratio of two subsequent numbers, and then shall we put this maybe here? The average growth factor would be then the geometric mean of our growth factors. The average growth rate is then this minus 1, also in percent, and then the forecast. Let's start also with the first value we have, and then we will move on now with the average growth rate. So this will be then this times this, and this we have to fix. And now we want to do all 4 quarters. And this would be then our forecast. Let's have a look how it looks like. And then, of course, you see that this is really then a smoothing because you have only a constant growth rate per quarter. Again, because otherwise I always write it in the diagrams of the students that we know what we are showing. This one. And what else? The yearly forecast. This we had here. This was our data. And again, the growth factors. I think this should work, or no. And then this one. Oh, it doesn't change because you have only zeros, of course. Then he is ignoring these zeros. And then we have this as the starting value, and this is not C, but G. Well, and this number we shall compare with this number here, and this would be just the sum of these values. Well, and of course, both methods are reasonable ways how to forecast the whole year 2023. I cannot say which one is the better one. Both methods are reasonable ways how to do it. Okay? And then it is again your task to find a reason why you choose this, or maybe in the end you average both forecasts. Yeah, this is up to you. And let's also plot this here. Mm, And this is also the forecast. Yeah, that you have all this at one slide, we will put it here. It's up, up, and maybe this is also all in red, and this also in red. That you remember that this is a forecast. And this is weg. Und tada. And now we are done. Well, and producing such tables and such nice little diagrams, this was my task for about 5-10 years. Analyzing any market. When I have worked for the Handelsblatt, we were experts for almost everything. Okay, so properties, quite clear. Well, if we see this clear trend, then this is a reasonable method. Also, this is quite often done because it's just an easy method. And therefore it is also used as the first idea. Where could it be? And also for, for a longer forecast. So not a nowcast. You will not find this method very often. But yeah, if you go for a longer time, and of course, if you have, let's say, 3 years monthly data, so 36 data points, and then you have 2 or 3 outliers within this time series using the average growth rate, then more or less your outliers will vanish. So if you want to smooth your data in a way that you do not very much rely on these outliers, then quite often this method is used. But of course, yeah, the starting point here is always very important because you are, yeah, going calculating backward. Then of course you always see your starting point is the anchor where you are coming from, and therefore, and there you have to be a little bit careful that it is very sensitive if your starting point would be an outlier. And yeah, in macroeconomics, this is was or is still very reasonable. If we go back in time, then we have Corona, and there we have these huge fluctuations in GDP of plus minus 10% within one quarter. In the shutdown, minus 10%, then opening in the summertime. And then if you just move to the next data point, then your forecast would end up somewhere totally else. Because then it is very sensitive to this. There, one has to be a little bit careful. So, last thing, and then we are through with this, is seasonality. And as we have seen in our series, where is you're starting the black one here, then you see that I created a timeline which has a seasonal pattern. And yeah, and this means then if I want to forecast the next quarters, and I always know that the fourth quarter in history was lower than the third quarter, then in your forecast, it should be maybe not the case that for the next year, the fourth quarter is larger than the third quarter. And therefore, you want in general to get rid of, or that you analyze, well, what kind of pattern do I have always in every year? And as I mentioned it in the unemployment data, we see this, and yeah, almost everywhere in economic data, especially in my topic in macroeconomics, we have the seasonality if we have quarterly data. And for this, there has been developed a quite sophisticated method. And on this method, actually, we rely in the whole world. So in every country, we are using this method developed from the US Census Bureau, and right now it is X13. I think I started all my stuff there. It was X9, so it is always changed over time a little bit, and then they use here a new number. Well, we will not talk about this. This is then deep econometric stuff. I will show you just, yeah, a quite easy but hopefully reasonable way to get rid of this seasonality within your data. Well, what we can do is, if we say, well, we have always more or less the same pattern in every year, then I aggregate what we have already done for every year, my total revenue, and then I calculate for every single year the proportion of every quarter. Then, as I already said, the third quarter is larger than the fourth quarter. Then I will see that the proportion of the third quarter will always be larger than the proportion of the fourth quarter. And what I then again do, well, forecasting is quite often just averaging. Then I average over time, now over the years, every proportion. Then I use some method for a yearly forecast, which is in my eyes reasonable. This can be moving average, this can be average growth rate, exponential smoothing, whatever. And then you have an aggregate number for the year 23. And then we use just the average time pattern for the quarters. I think it is not that hard. I think we just do it and then you see what I have talked about. Okay. So again, our data. And now I will just rearrange it because I need the averaging for every year. This we have already done for 2018. We take the sum and now the proportion. And this would be then 330 divided by 1490. And this we are doing just for every year. And this we have to fix, and then I want to copy it. So I want to move horizontally. So the number should be fixed in this way. Hopefully this works. And oops, let's use again percentage. And so here we are, and I think we had already two. Then let's use for 23. We had once, oh, no. First of all, we need now the average of every quarter proportion. This I have forgotten. So we need now Q1, Q2, Q3, and Q4. And for this, the average, so 1 over 4 and this plus this plus this plus, oh, I have 5 years, plus, up, did I something wrong? This and divided by 5. Oops. This should work now. These are the average. And now let's 23, we had exponential smoothing with alpha 0.3. Oops. And 0.8. And this was this number and this number. And we had average growth rate. There we had two methods. We had one method with first forecasting every single quarter and then aggregating. And we had the method first aggregating, then calculating the average growth rate, and then forecasting. So this I will call then Q1 to Q4. Or maybe we can compare this. This is maybe nicer. We may only the yearly forecast, because then it's just the other way around. And this was this one. This were the forecasts where we have just written down, and here we see this. This I should have mentioned before. Here you see that the fourth quarter, of course, if you forecast with a constant growth rate, then of course the fourth quarter has to be larger than the third quarter. And now, first aggregating, then calculating the aggregated forecast for the whole year. And now we will calculate this number. Since I want to copy this, is then fixing the number times 2.26. And this should work. This is okay. Yep. And now this should then also work. No, this doesn't work because the letter is not working. So here we need always B. Oops. C and B. Is it not working? B20 times A14. And even this should be, no, this works. And the C is okay, but the A is wrong. So A has to be changed in B. And here, then let's copy this. And again. So am I right? 24.3% times 1,681. Okay. And then actually we went, so to speak, the other way around. First, using a forecast for the whole year and then taking back from our general seasonal pattern. And hopefully this is also reasonable. For you, this is a quite simple, but I think also a quite reasonable way to do this seasonal forecast. And in the end, that we can have a look what these different methods mean to our overall time series. We have now 1, 2, 3, 4 forecasts. So and these are our forecast methods. And then let's have a look like how it looks like. Have I done something wrong? I don't think so. Yeah, this is actually also quite nice overall. This then maybe for you when you are presenting next week. Oh, this I forgot. As the other groups has done have done. You should also look at some data set, maybe 20 data points or 20, 30 data points, something where you are interested in, and then just use all these forecasting methods. And yeah, maybe then you find here also something like this, because yeah, then in the end, maybe we would say that only the yellow and the blue one, now the blue one is the average growth rate, but then we have not this seasonality time pattern anymore, and the average growth rate using then the seasonality. Because with the other forecasting methods, we always had the case, since we rely more on the historical data, and especially the third quarter in your time series is quite high, then you're stepping only a little bit back. And this means you have a quite high level already. And this, using the other methods, means that you step quite more downward. So maybe then just looking what you are doing here with your forecasts would then mean that with the moving average and with the exponential smoothing, you would say, well, here I directly see this problem since I have this general increasing trend that I step too much downward with these forecast methods. And maybe by I, then you would say, in this case, I just take the average growth rate. Or what you then could also do is that you at first detrend your data. So you are calculating the average growth rate, and then you reduce any data point via this general growth rate you have calculated. Then you have a new data series where you have not anymore inside this growing trend, and then using moving average. So this is what I mean with just playing around also with different methods and not only using one. You can combine these methods, and what is reasonable is up to you in the end. Yeah. Okay. So let's put this also within the presentation. Maybe this a bit smaller. And this overall forecast. Okay, I'm again running out of time. I'm talking too much. Well, something about decision making. Well, here now for the forecast, we just took the data and then with some simple methods, we moved forward in time. And in general, yeah, in your company, you have the problem that maybe you have an idea what can happen in the future, but then quite often you have two different situations that in the one situation you say, well, although I have an idea, I cannot really reasonable specify this scenario will occur with 20% and the other one with 80%. You just have an idea something in this direction can happen, but I cannot weight this with 30 or 50%, something like this. And in such a situation, we would say we are in a situation of uncertainty. And then there will be situations where maybe also from historical data, we could say, well, if you have a classical experiment flipping a coin, then of course you would say the future probability of heads and tails is 50%. Or in economics, there you do not have quite often definite probabilities, but you have a reasonable way to estimate the probabilities of the states in the future. And in such a situation, we will call such a situation a decision under risk. Maybe you have talked about this also in other lectures. Okay, and now we will go through some different decision rules, once in a situation of uncertainty and in the other case of in a situation of risk. So let's think about a company. They want to expand to the Balticum. There we have three countries, Estonia, Latvia, and Lithuania. And let's say there was some analysis that these three countries could develop in a different way. And the first scenario would be, well, Estonia is performing quite good, will be still stable then the second scenario is Latvia, and the third one is the stable situation would be in Lithuania. So, and then you can think of a situation that your company has only the money to expand to one country. Well, and then we can form the matrix of all alternatives in one direction, and in the horizontal direction, the scenarios. So we have 3 by 3, then we have 9 possible outcomes. And then let's say you have just started as a young guy in this company, and then you should evaluate for all 9 scenarios, some number what will happen, for example, to the revenue of your company. And let's say in the end, this would be then the outcome matrix, and the numbers inside here is the development of the revenue of your expansion to the Baltikum. So remember, we have said that S1 is in Estonia. Alternative one was we expand to Estonia, and therefore then you see within the diagonal we always have the largest numbers. And if our expansion decision is not in the country where we have the stable development, then here I just have assumed that the outcome is lower, but not always in the same way, just for some reasonable evaluation. Well, and this you are then presenting the heads of your company, and you are talking about this, and all the calculations are reasonable, and then you have to make a decision. Well, we want to invest, we want to expand into the Baltikum. Where should we go? If you look at these numbers just by eye, would you have, so there is no right or wrong right now, but just looking at these numbers, would you just choose A1, A2, A3 for some reasons by looking at these numbers? Yeah, yeah, okay. Yeah, great. Yeah, yeah, great. Yeah, 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 sure. These two explanations will directly, and then I just redo this. The first two, yeah, general, but simple, but general and used decision rules. These are the so-called min-max and max-max principle. And but what one would do maybe, but we will see that we do not find this here. The very first step, if after the evaluation of these numbers, and this you have maybe done in game theory, is that at first maybe it is reason, maybe you can somehow reasonably kick off one of these alternatives. And for this, you use the so-called dominance principle. And there you look at the outcomes and ask, well, maybe one alternative is dominating another alternative in every scenario. But here, of course, since we have always the largest values at the diagonals, then this we do not have. But it would be maybe the case, it would be, for example, the case if here at alternative A2, we wouldn't have here a 70, but let's say a 150. Then 150 is larger than 140, 120 larger 55, and 60 larger than 55. Then I would say that A2 is dominating. And this at the first step you would do with all alternatives vice versa. And maybe then at a starting point you could simplify your decision process a little bit. But then let's go through this. Oops. Yeah, maybe I have this. I have somehow forgotten, or this is the problem in general. Since we have, and you somehow already solved this. If I'm very risky, then I'm just looking at the largest numbers, and if I'm very risk averse, then I look at the smallest numbers to decide. That yeah, in general, I have this uncertainty, and as we have seen here, I have no dominance within the alternatives. So in general, I cannot really compare the alternatives using all scenarios in parallel. So I have to think what is a reasonable decision rule for me. And this you have also already answered. This is up to my preference. If I'm a very risky person or if I'm not such a risky person or an optimistic or pessimistic one. Yeah, and about the first three, I have already talked, and maybe if my colleagues have already done this, then we can go through this quite fast. Have you heard about the other four? No? Okay, but they are also not very complicated. We just go through them. So, yeah. So, definition of domination. Um, This I already said. I compare in every scenario, and if in every scenario I have a larger outcome for one alternative compared to the other, then I can kick out this alternative. Minimax is what you have said. I look at the worst values I could get, and from these worst values, I then choose the largest one. And the other way around, Maximax, I look only at the best outcomes. And again, if this is my focus, then I just pick the maximum value of all maximas. And very astonishing, as we almost always doing this in economics, I choose something in between these two rules. So I'm looking only at the worst and the best outcome. And then I choose again somehow some kind of a preference parameter of myself, again lying between 0 and 1. And let's say the worst outcome is weighted with 20%, then I'm quite optimistic decider because I rely for 80% on the largest outcome. And then we are back in statistics. This is nothing else than calculating an weighted average of the worst outcome and the largest outcome. And again, I use the maximum principle that then I choose from these weighted average the maximum. And this is, I think also he got a Nobel Prize, Mr. Leonid Hurwitz. This rule is named after him, and he has done very much about decision theory in general. So then maybe we can do this at only one slide. Oops. No. Let's start. So, no. Yeah. So first of all, we can state that there is no alternative dominating another one. No alternative dominates another one. Yeah, then let's start with min-max. Maybe since you have already said this, so we look at these numbers here, and this then would mean that the 60 is the largest one. So min of A1, min of A2, and min of A3 is 55, 60, and 40, and this is the maximum. But as you see, yeah. Oh, sorry. Yep, you're right. I'm too fast. But as I heard it, you have done this already in your first semester, which is nice. So the second one, max. Then of course we look at all the diagonal elements, A1, A2, A3, and this is 140, 120, and 130. And we have here the maximum. And the last one, the Hurwitz rule. Well, and for this, then of course we have to choose an alpha. And let's say we start with alpha is 0.2, and it is, how did I define this? Choose which is the weighted average, but then I also have to say that A should be alpha times low plus 1 minus alpha times high, and alpha is element of 0 and 1. So in this case, I'm again a guy who always uses this one, Hurwitz. And if we have ups 0.2, then I have 0.2 times the lowest one. Well, I have two lowest one, but anyway, doesn't matter. Plus 1 minus alpha times 140. And this is alpha times 60 plus 1 minus alpha times 120 and alpha times 10 plus 1 minus alpha times, oops, 130. And let's also choose a high. So we are overweighting the low outcome, 0.8. And if I now press enter, what do you think? Which alternative will be done the best? Well, I suppose it will switch then to A2, since at the min-max principle we had also A2, because now we are much more pessimistic. Let's see. No, almost. So let's change this. We have to be a little bit more pessimistic. Let's change this to 0.9 so that we have this one. Okay, I think I directly copy this just in here. But then maybe what's nice if you have alpha, or then let's use this 0.8, and this you should then do next week, because we can of course do it also the other way around, not choosing it first in alpha, but calculating just the alpha where the alternatives or the best alternative due to this Hurwitz rule is shifting. And why is it also a good thing doing this? Because then you see, well, where is a more, so to speak, for pessimistic investors preferred alternative, and where is an alternative for more optimistic. So this split or this switching point, this has also then information for you. So because here at 0.8 we had here 72, 72, and the last one was I think I've did something wrong here, or oh no, it's because of the 10 here. Yeah. So the 10 really dampens then the outcome. Yeah, 13 and okay. And with 0.8 we had 34. Okay. So here at alpha equals 0.8, the decision just switches, and this is the Hurwitz rule. Okay, at the exercises, then you have also just an example doing this. Yeah, then Mr. Laplace, French mathematician, he has done very much about probability theory in the, I think, 17th, 18th century, and yeah, he went also quite often into the casino. He is known that he was really interested in playing cards and so on. And therefore, we find him here also in decision rules. And this is really the hard way. We just take the average of all outcomes and take the largest one of the average. But you see here, then in the Hurwitz rule, we didn't use anymore the information of the outcome in the middle. And this rule is using all data. Yeah. And there one has also a little bit careful. So what is reasonable for you? Averaging or specifically looking only at the endpoints of your outcome. So of course, quite often the first thing is we just use the average outcome, and this is known within the decision rule theory for Mr. Laplace. Mr. Krelle, in the beginning of the 20th century, I think, yeah, this in the end, then you know from microeconomics that somehow we say, well, what matters is not the number of euros which I have, but what kind of utility I give this number of euros. And then we could introduce just a utility function depending on our decision variable, so our outcome G. And what is then the analytical difference between square root and taking the square? What is the property of such utility functions? And what is the property of just, oh, this shouldn't be 4. There should be also a G behind it. So just some number times the outcome. Have you talked about this in other lectures? So what the curvature of the utility function has to do with decisions? How does it look like f of x equals square root of x, f of x equals x squared, and f of x 4 times x? How does these functions look like? Actually, this is a topic for the introduction into economics, into mathematics for economists. So how these functions look like. I always said in economics, you only have to know about, I think, 6 functions. Square root, square or exponent, some exponent, 1 over x, log, and exponential function, of course, and the linear line. And that's it. So square root of 1,605,855. Is this larger as this number or lower? Square root of 2 is 1.41. Square root of 4 is 2. Square root of 9 is 3. So you are always dampening. And in curvature, this means that is a concave, a right-banded function. And square means, of course, square of 2 is 4, square of 3 is 9, and so on. This is your parabola. It looks like this. And the linear line, of course, looks like this. Well, and what does this have to do with decisions, why is the Quelle rule then something else, is that in this case we dampening here very high outcomes, while in this case a very high outcome is, so to speak, overestimated, because a square of a large number is, even in absolute terms, much, much larger than a low number squared. So 2 square is 4, is plus 2, and 3 squared is 9, is plus 6. And this adds up always. Okay? Well, and here it's always relatively going upward in the same way. And here I think I did something wrong. After transforming with the individual, choose the alternative with the largest average is missing here. Because of course, otherwise it wouldn't change to the maximax principle. Yeah, and the last one is Savage-Nihans. Choose the alternative in which the largest disadvantage within the worst scenario for every alternative is minimized. So this is then somehow a concept relying on opportunity costs. Do you remember what opportunity costs is? Or the concept of opportunity cost? So this means my decision, what I am doing, the cost of my decision is not having decided for the second best alternative. And somehow I use this concept here, that at first I transform the outcome matrix, that I say, well, I have already, or in my mind, I have already decided. So I'm choosing the line, the alternative. And then I ask myself, what could have happened? Because I have 3 different scenarios. So let's maybe directly go this at the matrix, that you see this. So choosing alternative 1 means I lose at maximum 55. So if scenario 1 happens, then I have decided in the best way. So my loss is just 0, okay? But here 140 minus 55, I lose the possibility, although it is of course lower, I lose 55. So 140 minus 55 would be then my transformed value. And this then I do for every, but at first we want to calculate the other. Oops. Two. So, oops. First Laplace. This is not very hard to calculate. Oops, is then just the average of these three. See if this works. Then, so, well, in this case, I see as choosing alpha is 0.2 in the Hurwitz rule, I would be due to this decision rule indifferent. Between A1 and A2, and then let's go to not Laplace, but this was Grelle, and the first one was up square root, huh? Ugh. Even smaller. No, good. So then I take for every scenario alternative pair, the square root. And the average afterwards. So, and since we have talked about the properties of squaring and taking the square root, what would you think, or what is the possible outcome which is now best using the square? Or are you surprised that using the square root, we have the second alternative as the best one? Or wouldn't you expect that the best decision will change? So if I copy this and pressing enter. Yep. Yes. And why? Yeah. Yes. Yeah. Great. Yes. And especially A1 is with the maximax best. And here with a square, even this 140 gets a higher weight. And therefore, I think it will be the case. Yes. And we see it. Yeah. And of course, for this, you also say, well, this is a utility function of a person where the preferences you are a little bit more risk averse, because a very high outcome, well, still you say this is good. This is nice to have a very high outcome. But the slope here, the additional utility you get from a euro when you have already a very high income is much less than the additional euro you obtain when you are coming from a low income position. And here it is, of course, just the other way around. You are just seeking for the possibility to get a very higher income. And to be complete, let's also take the linear case. I don't know what is the outcome, something in between, of course. And where just the switch is, this also you could calculate that you are not using just square and square root, but just an exponent alpha. And again, similar to the Hurwitz rule, you could then calculate the alpha when the decision between A1 and A2 is switching. So this is 4 times the value. Oh, of course, here we already know the result. Because I'm multiplying every outcome just with the same number. And what did I already do? What I have already done? Yep. Yes, it's just the average times 4, so A1 and A2 has to be the same. Okay, nice. So I'm definitely running out of time. So I just ask you. I think I will make it through the decisions under risk roughly within 15 minutes. Is it possible for you? Yep. And oh, the savage knee hand. Maybe I have already explained it, and you show us the savage Niats rule. Look it also up in the internet, and you will make it. Yeah, and take then the example next week. Okay. Yeah, decisions under risk. I said it. Classical lottery, coin flip, throwing dice, and then, so to speak, using reasonable probabilities in the stock market process and in general in economic growth scenarios. So very, very often we use this, and similar to the Laplace rule, it is just more or less than the Laplace rule if we would assume that every scenario has the same probability to occur, then averaging everything would be just the expected value. And of course, if we know the probabilities of occurrence, then one decision rule could be, well, I just choose the alternative with the largest expected value. And this is near your personal topic. Well, in general, of course, we have these different scenarios. I think here now I took 3 or also 3, but it can be, of course, more. And then you have a fluctuation and the general measure, which we have all we have also talked about in the beginning of this course, is then just the variance or the standard deviation of our random variable. And then in general, we say, well, within our decision, we incorporate not only the expected value, but also the fluctuation. And this is the so-called mu sigma principle. And then one possibility, I will choose here only a very simple utility function. Well, you can say in general a utility depending on the expected value and the standard deviation would be that you just take the difference between the expected value and the number times standard deviation, but be careful. A can be larger or also less than 0. Well, in this case, if we have defined it with the difference, and we would say this A is larger than we are subtracting the standard deviation, and this we can compare with these utility functions here. What kind, if we say this is risk averse, this is risk loving, and this is risk neutral. What kind of investor would you be if this A is larger than 0? So if we are subtracting the standard deviation. So this would mean, well, I do not like really fluctuating outcomes. Well, this always means I want to go to holidays and do not care about my investments. So this would be then that I'm more or less risk averse. If it's less than 0, then I add standard deviation. Then the more my investment is fluctuating, the more I add, the higher is my utility. Then again, as in these examples with uncertainty, I really seek for alternatives with this 140. This I want to have. So this would be then risk loving. And of course, then A is 0. I don't care about the fluctuation. This would be again risk neutral. And the Bernoulli principle, this is the same as Krelle, but we have to admit that Mr. Bernoulli or all his brothers, I don't know on when, after which of these very famous guys it is named. There were, I think, 3 or 4 brothers in Switzerland in the 18th century, all very famous mathematicians. This is again, well, we use again a utility function, and then we use, as compared to the Credit rule, just the largest expected utility. Okay, 7 minutes left. Let's see if I make it in 7 minutes. This is then risk. A little bit smaller, as I need something. So this would be now our situation, and now, well, I called it the first part S, so I should do it here also. So expected value. How do I calculate this one? What are you doing? For the first alternative, yeah. And yeah, and then yes, and add up. Yeah, of course. So this and this I can copy down it. Then the number to have to fix times this one. Oh, sorry. Plus up this one times this plus this times this. So then, of course, I would use my stocks, the standard deviation. How do I obtain this? Hmm? This you should know. Sorry. No. We are in the 4th hour. It's okay. Variance. I have to calculate all squared distances, multiplying this with the probabilities, summing up, and afterwards taking the square root. So that's maybe it works a little bit faster. This minus this one and and now the letter and hopefully can this be true? This is 9 and 37 squared is also reasonable. So these are also the squared distances, and then let's calculate the variance is, I think, this one. Is this true? Yep. So every number times the probability and summed up. And then the square root. Yes. Let's done. Let's take an a equals 1 and let's, or a little bit more, not 1, and a risk loving one, a equals -2. This would be then mu minus a sigma. And then we have mu minus sigma, and in this case is mu minus 2 times sigma. What do you think? What will be then the best alternative? Do you have already a feeling? So after the expected value principle, we have just the expected value, of course, largest one with the stocks. Minus 2 means a risk-loving person, so I'm seeking for large volatility and just having a look at the number, which one will be now the largest one. Just also without calculating it explicitly, yeah? The second one, really? Yeah, it's plus for everybody, for every alternative. We add now sigma or 2 sigma. Yeah, yes. It has the most deviation and it has the largest expected value, so it has to be the largest number. Okay, and then let's do also one Bernoulli for this. Let's do, I think this is possible, or? No, I don't know. Therefore, I copy this. And oops. Also, Bernoulli should it be. And then let's copy this one and here. Oops. And well, using again a risk-loving one would of course doesn't change anything. So let's use a risk-averse one. Let's take square root. Doesn't work. Then I think the 100 is too large. Then let's use 1/8. Still not working. So I haven't chosen a good example. So no. This is larger than this, and this dampening here. Or is it even not possible with just an exponent? Let's see. No, unfortunately, this is due to the numbers. that the discrepancy, I think it even doesn't work with 1,000. Let's see if the log functions. Do I have numbers smaller than 1? No. No, it even doesn't function. I would have to think about why it cannot switch. So this would be in general the case if you have only a concave function. And since I have a monotonic transformation of the numbers, let's try one. Maybe the 40 over 2 is enough. That my argumentation was not right. Is this to the power of 10? Oh yeah, then it's the other way around. So this is a little surprise for me, since I thought, and there you see that you can make mistakes, although you think, well, I have done this quite often. So what we see here is that it is not possible to change the the direction of the row of the alternatives using a risk-averse function. And I thought, well, I have here this large outcome of 100, and this mainly drives the outcome using just the average. Okay? And therefore I thought, well, if I dampen this 100 with a risk-averse utility function, then at one point, alternative number 2 will be the best one. But maybe if you remember, then I used x to the power of 1 over 100, so the 100th root of our outcome. But it is here just the other way around. And the reason, if I think about a little bit longer about it, it is then in the end clear that it has to be like this. If we take a risk-loving utility function, as I've done it here, now to the power of 10. And the reason is the discrepancy between these two numbers here. Because 40 is 4 times larger than 10. So the upshift, the relative upshift with the risk-loving utility function over increases always by 4, this value over the value 10, while 50 in absolute terms is by 50 lower than 100, but it is only half of 100. And so squaring, taking the power of 4 or now the power of 10 will of course increase the 100 and also increase the 50, but the difference in the development between the 50 to the power of 10 and 50 to the power of 100 is in the end then much less compared to the increasing difference coming from these two numbers. So let's then take this. Oh, now I'm 10 minutes over time and I'm done. Sorry for this again. So, but I will put this also in and this is Bernoulli. And that you can remember this, that this number here is 100 to the power of 10. So the utility function is g to the power of 10. Okay, just go through the exercises and then you will see it's just redoing what I've done here. The last one is about the certainty equivalent. The last task I gave you, this is also a little theoretical task, but this you will also find. It is not that hard. Okay, thank you very much for your patience today. Thank you. You should have opened your micro, then we would have heard you. Sorry. Okay.